Host, please proceed.
And good day. My name is Roopnarine and I will be presenting to you on our paper, Smart Farming, Organic Communication Channels. Let's get right into it. What are organic communication channels? Organic communication channels, or OCCs, are any hydrocarbon-based media which can be used to communicate data. So this can be plants, animals, even you and I. Extensive work has been done to characterize the human body and soil-based organic communication channels, utilizing the electric and magnetic fields as propagation techniques. However, little work has been done to characterize vegetation-based OCCs. Why should we be investigating OCCs in the first place? OCCs offer tremendous potential when incorporated into cyber-physical systems for smart farming-based applications through the use of organic area networks. Now, how do we know this? When compared to RF technologies, for transceivers communicating using the human body, these transceivers achieve higher data rates, better security, greater spectral efficiency, as well as power efficiency. So it begs the question, why not apply existing technologies such as what has been done for human body communication, or HBC, to other organic channels? For this to be done, the feasibility of these organic channels need to be investigated. For the feasibility evaluation of OCCs is contingent upon channel characterization and the proposal of a physical layer infrastructure. To accomplish this, our paper intends on establishing the relevance of, feasibility of, and proposing the infrastructure for organic communication channels. So we set the foundation for OCCs through static channel characterization of vegetation-based OCCs and soil-based OCCs, as well as we propose a standardized framework for OCC communication. We also establish the relevance of OCCs beyond the current use cases through consideration of the Internet of Farming, or IOF. Some of these use cases. These here are just a few. As you can see here, organic communication channels can be used to communicate sensor data. So things like soil moisture and surveillance information can be sent through the soil. You can also obtain the channel state through channel sensing. So we can diagnose things like diseases in livestock and crops, or even track the growth stage of plants to improve yield. Further, we can see here that we could use OCCs to supplement RF-based strategies so we can improve channel resilience. And finally, OCCs can serve as an emergency means of communication. For example, rescue responders can utilize soil-based communication to communicate with survivors underground. Because, as we know, RF-based techniques don't perform as well in underground-based communication. So what now? We survey the literature to see the state of the art with regard to organic communication channels. From the literature surveyed, the only OCCs that were investigated were soil-based and human body-based. With regard to the soil, the magnetic induction technique was utilized to communicate information. This is similar to how a transformer works. So it involves the use of magneto-quasi-static fields which passes through the organic channel. The current in the transmit coil induces a change in magnetic field which is coupled to the receive coil, inducing a current there that is modulated with whatever data we need to send. Human body-based communication, or HBC, utilize either electric fields, termed EHBC, or magneto-quasi-static fields, termed MHBC techniques. EHBC techniques can be either capacitive coupling or galvanic coupling. With galvanic coupling, a differential modulated signal is applied between two transmit electrodes. Then induced galvanic currents are then collected by the two receiver electrodes. With capacitive coupling, the induced signal is controlled by an electric potential caused by leaving one of the electrodes of the transmitter and one at the receiver floating. Now that we have covered the use cases and the related work, let's look at the channel characterization. This is the setup that we've utilized. As you can see here, we use a vector network analyzer. This was used to obtain S parameters or scatter parameters for different lengths of OCCs over the HBC band or the 21 megahertz band. The HBC band is standardized, so it was our hope to adapt that form of communication to all organic or OCC communications. This data was then used to derive a log distance fading model. We investigated loam soil to cover soil-based OCCs, a papaya stem to cover herbaceous vegetation-based OCCs, and a coconut stem to cover woody vegetation-based organic communication channels. The electrodes, as you can see here, utilize both electric and magnetoquasistatic fields to communicate. These are some of the results here. As you can see, we plotted S21 versus frequencies for the different organic communication channels. As you can see here, vegetation-based OCC's frequency response can be approximated to flat fading for the HBC band under the channel lengths investigated. Soil-based OCCs over short channel lengths exhibited a relatively flat fading over the same frequency range, although having relatively higher channel losses when compared to the other OCCs. From the path loss plots, we can see that soil-based OCCs over longer channel lengths display significant variation in path loss over the frequency range investigated. Alternate signal paths between the transmitter and receiver can cause the fading observed. This has been corroborated with the research surveyed investigating HBC communication. Empirical results obtained here are comparable with channel losses for human body communication, pointing to feasible communication since HBC is standardized. We have our channel model for these OCCs. We took the IEEE 802.15.6 standard, which is the standard for human body communication, and modified it to produce a universal physical layer specification for organic communications. The BER curves or bit error rate curves were generated using the proposed OCC PHY infrastructure and a channel model for feasibility analysis. From the data rates seen in these graphs, we can see that text, voice, as well as low quality video transmission are feasible with OCC system. Specifically, an OCC system employing this physical layer infrastructure. So we can see that organic communication channels or OCCs offer great potential when integrated with cyber-physical systems as seen in the examination of the use cases for smart farming applications. Vegetation-based, that is herbaceous and woody, and soil-based OCCs were characterized. The log distance linear model was used to attempt to fit the magnitude responses for the OCCs investigated. The magnitude of the path losses suggests OCCs may be well suited as an alternative to short-range RF communication if there is an organic channel between the transceivers. The proposed OCC PHY layer showed feasible communication is possible using OCCs. In this work, we only looked at static channels, so we didn't look at things like, for example, if the moisture content of the soil varied. So in further work, we propose dynamic channel models be investigated for more channel types. Further, the MAC or medium access control layer for the IEEE 802.15.6 standard should be modified for all organic communication channels. These are some of the references. Thank you for your time. You can
Okay, thank you for that, Iran. I don't know whether we have anybody here to answer questions.
It doesn't seem like that. No, but I tell you what, I will never look at pawpaw and coconut the same way again. That has been very, very enlightening. It's unfortunate that they're not here to take any questions, but for our audience that do have any questions, please take note of the email address for Aaron, and you can contact him accordingly. But given that we have a few minutes, Terence, I probably want to go back at, there's one outstanding question from the previous section that we may be able to touch on. So that question was, would the most appropriate PDF change depend on how far along the country is towards a smart grid? So it's a good question. To be quite fair, the two things are two separate issues. How far the country is along towards a smart grid is totally different to the most appropriate PDF. And in this case, as the author had suggested, what we're looking to do is model that consumption of energy. So it's very, very different. But at the end of the day, what we're looking for from that previous presentation, which, I mean, I am an author, so I can talk a bit about that, is an opportunity to help us model what these loads would be given foreign data, because that's all we have available, and try our best to get a shape that will be representative of the local landscape. Whether that will be a best fit for the local landscape, it's a start at this point. So what we're trying to do is create the infrastructure to move it along the modeling side. So when there is some estimation of power consumption, we have a better appreciation of what the load will look like. So just thought it would be useful to share that and at least clear off that last question.
I have a question for you, since we have to use up this time. I just put it there. How did you, it's a behavioral model you use, right?
It is behavioral.
Right.
Correct. It is.
And you said that you're going from exploratory to confirmatory, right?
Yes.
But
yes.
How did you come up with initially the exploratory variables?
Because we know that at some point in time, the electric vehicles are going to be flooding our market. It's just a matter of when, as long as the local landscape can foster that change. And we're getting there. But in the absence of real data locally, the only data sets that we can access are those which exist in territories abroad that unfortunately have different power system landscapes, which would include different incentives to influence the consumption of behavior. They may have different pricing schemes, they may have different time of use schemes, and they may also be driving different distances. But we have to start somewhere. So from that particular perspective, let's look and see what the data gave us from a very broad perspective, look at it, try and model it, and then hopefully, as the author said, we could move towards a machine learning approach at some point in time. So I hope that addresses that question.
The only thing is that the data set is not really based on our situation. That's the only concern.
Correct. Which is why we're just looking at the charging scheme. How often do they charge? How long would they charge? So you could work backwards to determine, well, what would have been the influential aspects for that particular landscape, and then try and extrapolate it to the local landscape. So we need something. So we thought it best to start there and then compare to what we can from what limited data set we have within the local context.
Okay, good.